There are several types of bitwise operators, including bitwise AND, bitwise OR, bitwise XOR, or bitwise exclusive OR, bitwise NOT, left shift, right shift. All of these work on bits and perform bit level operations. Namely, if we have a two variable here, for example A and B, we just assign it 5 to A and then assign it 9 to B. Then this is the binary representation for 5 and this is the binary representation for 9. Now, let's see the first one, namely bitwise AND. What is bitwise AND? Actually, in the case of bitwise AND, we just compare each bit of two numbers and returns 1 only if both bits are 1. Okay, meaning we have two numbers here and this is the binary representation of the two numbers and we just compare corresponding bits. When we compare it, only in the case of both bits are 1, we just return 1, otherwise we return 0. That's the rule. Okay, I repeat again. Compare these two numbers in terms of bits and returns 1 only if both bits are 1. Otherwise, we are going to return 0. Okay, let's see it. We are comparing this bit is 1, first bit, this is the 1, therefore we just return 1, and this bit is 0, this bit is 0 because they are not 1. Therefore, we just return 0, and in the case of this bit, this is 1 and this is 0, therefore they are not both 1, therefore we just return 0. This is also same. Therefore, when we take bitwise AND between this A and B, the result is 1. Namely, A and B in terms of bitwise operations, the result is 1. This is the result. Actually, this is the binary representation of 1. Okay, now let's see the second, namely, let's see the bitwise OR. If we have a two condition, the first condition is true, the second condition is false, at that time it's okay, true, because one of them, either one is true, it's okay. Therefore, bitwise OR compares these two numbers in terms of their bits and returns 1, at least one bit is 1. We are comparing two bits, for example this bit and this bit, or this bit and this bit. Therefore, return 1, at least one bit is 1 among the two bits we are just comparing. Okay, let's see. In the case of this bit is 1, this bit is 1, because at least one bit is 1. Okay, both bits are 1. Of course, we return 1. In the case of this 0, 0, this is return 0. In the case of this, we are comparing these two bits and at least one bit is 1 because this bit is 1, therefore 1. In the case of this is 0, this is 1 because this is belong to the at least one bit is 1, therefore this is 1. Okay, therefore A or B, and the result is certain because this is the binary representation of certain, or this is the binary result of the comparing two variable A and B. Okay, now let's see bitwise XOR or bitwise exclusive OR. In the case of bitwise exclusive OR, we are going to compare each bit of two numbers. We have each bit of two numbers and returns 1 if the bits are different. Only bits are different, we just return 1. This bit and this bit are different, therefore we are returning 1. This bit and this bit are different, we are just returning 1. This bit is of course 0, In the case of 0, we just return 0, but this bit and this bit are same, and they are 1. This time, we just return 0, because this is exclusive. A exclusive or B. The result is 12. Because where this result comes from? Because this result comes from the bitwise operations between the 5 and the 9, namely exclusive or between 5 and the 9 is equal to 12. Okay, now let's see the bitwise NOT. In the case of bitwise NOT, we just flip all the bits of the number. For example, if we have a number 5 here, this is the binary representation of 5. Now, in the case of bitwise NOT, we just flip it. For example, flip means we know that because this is a bit and this bit, only two options, 1 or 0. When this bit is shown 1, we flip it, it of course shows 0. Therefore, this is 0. And then this is showing 0. And when we flip it, it should be show 1. And this is 1. When we flip it, it will be 0. And this is 0. When we flip it, it will become 1. Just flip it. Okay, just like a coin. It's front and back. The 1 is front and the 0 is back. Therefore, we just flip it. And then this is 5. When we do the bitwise NOT, it will become -6. Why? Because I am declaring this 5 in data type. Actually, we know that int data type occupies 4 bytes of memory. Therefore, actually, this 5 is int. Therefore, actually, we have 32 bits here. This is the first, second bit, third bit, fourth bit, and we have fifth, the sixth, and the seventh, ninth, and until here 32 bits here. Then, because this is 5, only I just show in terms of space, I just shows only the first 4 bits of 5. Then I just flip it. Actually, there are 28 bits here, but the 28 bits is all 0. When we flip it, of course, they will become 1, because we are just flipping it. And actually, they are representing the sign. Now, let's see the left shift. Left shift means is shift the bits of a number to the left by the specified number of positions. Zeros are shifted into the rightmost position. I just prepared the definition and let me paste it here. Okay, actually, left shift means is shift the bits of a number to the left by the specified number of positions. Zeros are shifted into the rightmost position. Okay, this is the left shift. For example, this is the number we are going to shift 1 position to the left. Namely, shift the bits of a number. This is the bits of a number 5 to the left by the specified number of positions. This is 1 position, specified number, 1 position. Zeros are shifted into the rightmost position. Zeros are, at the result, zeros are filled with the rightmost position. This is the rightmost position. Now, let's shift it, because we are going to shift this 1 to the left, 1 position to the left. For example, in the result, this will be, now this is the first bit, and this first bit will become the second bit, because we are going to shift it to the left, and then this will become here, this will become here. But the rightmost position, because we just shift it, this is the first bit, and there is 0, therefore this position fill it with 0. This is the meaning, or this is the rule for left shift. Then this is the result of the left shift of 5. Okay, 5 and 10. Let's see here, left shift 1 position actually corresponding to multiply by 2. Okay, we have a number or we have a variable 5, then we multiply it by 2, it's equal to 10. Namely, left shift the number is equal to multiplied that number by 2. Okay, double that number. Okay, that's it. Then let's see the right shift. Actually, the rule is same, but direction is different. Okay, the first one is shift to the left, the second one is shift to the right. For example, we have this variable b and its value is 9. Now let's see the b shift one position. Okay, shift the bits of a number to the right by the specified number or position. For example, one position. At this time, the leftmost position are filled with the sign bit. Okay, let's do it. Okay, we just shift this left. Okay, because in the left there is no position and this is gone. Okay, this is come to the first position and this is come to the second position, and the fourth position comes to the third position, and then the most left position, this position, fill it with 0, and this is the result. Therefore, we just seen that bitwise operators. Bitwise operators is very important. If we properly use bitwise operations, we can speed up the execution speed of a code. We just saw that here, left shift one position is actually equal to multiply by 2. Namely, in computer, the multiplication and the division is very expensive. If we properly use this kind of bitwise operations, at that time we can speed up the execution of a code. Therefore, bitwise operators is very important. Actually, I have added some helpful information to this figure, namely this bitwise operators figure, in order to make it easy to understand them, especially to the left shift and right shift portion of this figure. I also added some information to the bitwise note portion as well. Namely, added some arrows to the left shift portion and also added some arrows to the right shift portion as well. Namely, these arrows help us to understand where this bit will be moved or where this bit will be shifted. Therefore, this information make it easy to understand them. And then also added this information because in the case of left shift, this position should be filled with 0. Therefore, I just added this information for this position, and then in the case of right shift, this position actually should be filled with 0. Therefore, added this information. Then, in the case of bitwise note, this process is actually flips all bits. Therefore, just added this information. Let's see example. Okay, this is example. Actually, we just see these examples in here. Actually, we have A and we have B and 5 assigned to A, 9 assigned to B. Okay, let's see in detail. First is bitwise AND, bitwise OR, bitwise exclusive OR, bitwise NOT, left shift one position, right shift one position, and these are the results. We just saw that in the previous section in the explanation. Okay, now let's run this code and just display this in the standard output. Hopefully these kinds of results will be displayed. Okay, now let's run the code and this is the result. Okay, let's see that the 1, 1, 13, 12, minus 6, 10, and 4. Okay, this is the results. Okay, therefore in this section we just learned about the bitwise operators. Bitwise operators are very important. If we properly use bitwise operators, we can improve the speed of code.